I want to talk to you all today about this topic because it's pretty near and dear to my heart. I've been practicing as an engineer for about 20 years. We get a lot of young engineers coming in. We try to help them and mentor them. And what I really find a lot of times is we're missing this piece of the finite element model, which is the actual engineering piece of understanding what you're doing, understanding what you're analyzing, what you're modeling, what you need to expect of the behavior, and then implementing the design. Because if we just hit run, take the results and design, we're really asking ourselves to make big mistakes. And we do a lot of forensic work. I keep waiting for the day when unfortunately something's going to fall because we're not doing this step. And we're not understanding how the computer model got into equilibrium and understanding what we're designing. And so I'll try not to lecture too much, but I do get about a half hour here to try to do that. There's some great textbooks out there. Artie Cook has some really great quotes that I'm trying to paraphrase and steal. We're going to go over that. We'll talk about quality control versus quality assurance, how it fits into that process, and where do sanity checks fit in. We'll talk about what I have a sort of a working definition of what I'm calling sanity check. It's mine, and we all should have more conversation after this session because I think it's a really good topic. When they should be performed, the goals and benefits, why we're doing it, the importance of performing the sanity checks, and examples of sanity checks in practice on a structure. So I'm going to talk about a self-sinking case on investigation we did. This text had some really great pieces I took from it. One of it is that seasoned practitioners, they always stress that you need to have, in order to have reliable results, the person who's doing the analysis needs to understand the problem and how to model it. They need to understand the behavior of the finite elements themselves that they're using, and the assumptions and limitations that are built into the software, as well as the input data formats that they're using. And they need to understand those so that they know that they're designing, you're going to use the results, and you're still going to need your engineering mind to design things. I hear it a lot in our company sometimes. The older engineers like to go back in the day and they complain a lot. But they complain a lot about that younger engineers sometimes just trust the model. So they'll run that model, it'll be a great, pretty picture, and they're just going to trust it. And when a seasoned practitioner looks at it and they say, well, this doesn't even make sense. What's my total static moment? It's not, something's wrong. And then we go find the mistake. And that's really the sanity check piece. Does the results make sense? You can use analytical skills that can really be developed by analyzing the problems in the results, by using hand calculations that they've used all the way back into the 1800s, 1900s, to just see, does it make sense? Even though you have a complex model, it still should be in that same ballpark answer. You need to have an understanding of the ballpark. And that sometimes crude methods can really help you identify problems in your model and really short circuit your QA, QC of that model and finding that there is a mistake. So I'm going to go in here now and talk about quality control and quality assurance. I don't love the Webster Dictionary for engineers in the modeling. They talk about quality assurance as the program for the systematic monitoring and evaluation of various aspects of a project, service, or facility to ensure that standards of quality are being met. And quality control is that aggregate of activities such as design, analysis, and inspection of defects designed to ensure adequate quality, especially manufactured products. I did really sort of resonate with me with this ISO 9000 standards, which quality control is a part of quality management focused on fulfilling quality requirements. It's the checking. Where quality assurance is part of the quality management focused on providing confidence that quality requirements are going to be met or fulfilled. So are you making sure that the quality control is being done, if that makes sense? It's a little bit academic, but it is sort of important to understand what that QA, QC piece it stands. And then as a sort of brief introduction to sanity checks, it's really a basic test used to quickly evaluate a finite element model to confirm whether the results represent realistic behavior. It ensures that the model is working as expected. It confirms whether the model is providing results that make sense or are sane. It involves engineers evaluating the results at important features of the model at critical locations and comparing their understanding of the expected structural behavior to what they're getting. I'll tell you, I'd say about 70% of the time, there's a problem with the model, and another 30% of the time, I say, wow, I didn't think about the compatibility of deformations, and so I teach myself to get it right. So sometimes the model's right, sometimes the model's wrong, but you at least going through that process, you'll become a better engineer for it. And then require engineering judgment. I know we're trying to get more and more into AI and doing a lot of analytical work on the computer, but you still need your judgment to make sure you get things right. And performing these sanity checks will really help you along the way, getting that judgment. I'm going to sprinkle in some picture slides here, just so you don't have to listen to me just talk all the time. But this is one type of sanity check that I make sure that our young engineers and I do every time. If someone asks me to QC a model, I don't go to the inputs. I start looking at things like the exaggerated displaced shape. This picture on the left happened to me about 2 months ago. A young engineer was modeling a concrete slab on beams. They modeled the beam, you can see here in the undeflected shape, as a frame member, and they modeled the slab. They offset the slab. They were really excited about it. I said, have you looked at the overall exaggerated displaced shape? And they said, well, no, but I'm not looking at displacements. I'm looking for forces. I said, please look at the displacements. And when we looked at it, you can see right away that the beam is not tied to the slab. The nodes weren't aligned. And if you exaggerate those displaced shapes, it'll become pretty obvious. What's going on? This doesn't make sense. It doesn't look right to me. It's not sane. Sanity check. Another case was a garage you have ramps. You have a lot of detailing that you need to do. You can see right away that beams are supporting the slab. You can see the deflected shape, but you can also see some significant torsions down here. I'll put it here. You can see some torsions of this beam. You can see some additional sort of gross displacements, and that really can help you identify issues with your design that, hey, wait a minute, do we need another beam here? What are we doing? Why is this beam twisting? Do we want it to twist? Have we designed for it to twist? Have we put the torsional reinforcement in this girder to allow it to twist? Because the model doesn't know these things. It's going to do whatever the restraint conditions that you've applied to it. Now, you as a designer need to think through that. So one of the things that I suggest is whenever you get a model, look at the exaggerated displaced shapes. And don't worry if you're exaggerating to a point where it's not realistic in terms of magnitude. You kind of want to exaggerate it so that you know what's happening. I think it's important to sort of touch, sanity checks are not detailed verifications. I'm not asking you to go through and look at all the inputs. Did they input it right? That's part of the QC process. It's separate. Sanity check is looking at the output saying, does it make sense to me? It's not a detailed test or check of the inputs or modeling decisions. It doesn't take the place of a comprehensive quality control assurance process. And the point is to really rule out certain classes of obviously false results and make sure you get this right. So I really think that it fits into every QC process. And from a quality assurance, your program should be confirming that they're happening. So you need to confirm that the engineers are performing sanity checks. Have you looked at, the display shape? Have you looked at a 1G total static check? And putting it all together, I think that the sanity check is a basic test used to quickly evaluate whether a claim of the results can be possibly true. It's a simple check to see if produced material is rational. The point of a sanity check is to rule out that certain classes are obviously false. This is not right. This is not what I wanted in the model. I've got some error that I need to fix. A sanity check introduces the intuition that can really help that designer then reinforce your concrete structure correctly and get the behaviors that you're modeling to actually happen in reality. And they should be performed early and often, and they really don't take that place of that detailed verification. So don't just do sanity checks and say, I must be fine. You want to still check your inputs. Some of the types that we use in practice, we investigate the exaggerated displaced shapes, like I already mentioned. We look for the overall displacements and the discontinuities of the displacement. We will look at mode shapes. Whether you need the mode shapes or not, look at the mode shapes. Make sure that you don't have parts of your model disconnected, getting behaviors that you didn't expect look at multiple modes, look at the frequencies. You can run simple calculations to understand what you expect. Just make sure you have things correct. You want to investigate the axial forces. I think this is especially important for concrete because there's compatibility of deformations that can create axial forces in your flexural members. It does impact the behavior. Sometimes it's right, sometimes it's wrong to how you've modeled it, but you want to understand that it's there. Anyone who offsets a slab and has a beam frame member underneath it, there is a chord force that develops, axial force in your beam and your slab. And if you just pulled the bending moments out of that beam frame member, you would not have the correct bending moment that you're designing for. So if you did a simple WL²/8 check, you'd say, oh, wait, that moment's not right. But when you accounted for the axial forces, you'd get it right. You'd have the right value. Summing the overall base reactions for where you think the lateral forces are coming out in your model and making sure that you don't accidentally have restraints in your model that are dragging forces where you didn't want it. This happens on garages. Sometimes I see it a lot where the ramp acts as a shear wall if you're not careful, if you're not detailing it in the field and in your model consistently and correctly. Viewing the principal stress contours and trajectories are very helpful. And then running total static moment checks and just rule of thumbs, back of the envelope calculations are always helpful. So a static 1G analysis, that's just, you've modeled it, you might as well run it with just gravity and just understand what's happening. Look at the deflector shape, look at the expected reactions. It's a very quick check before you add a lot more complexity, that you don't have some mistake that's happening, a very rudimentary mistake that you may have the wrong material that you've accidentally applied to some of these models. Looking at the principal stresses and stress trajectories, it's not showing up maybe great on the screen right now, but can be very helpful. In this case, this investigation that we did, we realized that there was a pretty big strut action happening from the principal stresses and a tie that was happening as this ramp wrapped around. And so we ended up suggesting some additional reinforcement get placed in an area that you may not have thought about if you didn't look at axial forces and principal stresses. Another, maybe from the same project, was a column with two sort of large girders. The girders that I was mentioning were in torsion and the one exaggerated display shape. What we found here is the compatibility of deformations created some Varendale type action. We were getting high compression in the top and high tension in the bottom. It explains some cracking we saw in the field. And it was a case where one of our younger engineers said, we're getting huge axial forces. I don't understand why we're getting it in the model. And as we thought about it, we said, well, it's real. And it's actually helping explain what we're seeing, why we're seeing the same two girders carrying the same load. One's cracking, one's not in the field. One's in tension, one's not. So it helps you build up your understanding. Doing this modal analysis, some simple hand checks for what frequencies you expect, seeing what those frequencies are. And then when you look at these mode shapes, exaggerate them a bit, make sure that everything that you intended to be behaving together is, because you'll catch that in the mode shapes. If you thought one piece was a connected one or shouldn't be connected, you'll pick that up when you look at the mode shapes. Again, repeating myself a little bit here, but early and often, before you do the detailed review, I suggest doing sanity checks. And before you add complexity, so don't just jump to complex. Build your knowledge of what's happening as you go and do some sanity checks along the way. You'll be a better engineer for it at the end. And then this goal is to define the expected performance. You want to save time and cost by fixing modeling errors quickly. Instead of having a senior engineer looking at all of the inputs, a lot of times just looking at whether it makes sense or not will find errors for you. And then that will really greatly speed up your checking process. It quickly evaluates the basic functions and introduces the intuition, which I think is the most important part in the process. And it makes sure at the end of it, whether you find any errors or not, the engineers now understand the model output and what's happening. And I think that's crucial to the design. And again, I've just now still just feel like I'm preaching again, but it just forces us engineers to understand what you're doing and making sure you then make good modeling decisions. So I'd like to jump here. Well, boss, how am I doing on time? About 5 minutes? Okay. So I want to go into an example where we really we built simple to complex. Simple to complex, and it was a very complicated problem. And I will say that by building from simple to complex, we were able to stop when it was appropriate, not overanalyze the problem, get the understanding of the basic behavior, and at the same time, I think get the right decision making in this investigation. So this was a self-sinking caisson. I don't know for everyone who's familiar, but they basically build these large shafts up above ground, and then they get them to sink under their own self-weight into the ground as they go. The photo here on the left is one of our principals. He just retired recently. But that's a crack that's measured in inches, not fractions of an inch. So it's a delamination crack that was about over 12 inches wide. The structures are pretty massive. It's 136-foot diameter. The walls are 7 foot thick. Here's some reinforcement cages. You can see they were like number 11s at 6 inches on center, front face, back face. And this is the stage where they built the first two stages, and they built it on timber cribbing. Once you get the first two stages, you pull the cribbing out, and this thing starts to sink under the ground as you're building the next stage, and you keep building and getting it to keep sinking. It really involves a lot of soil structure interaction, geotechnical work that you have to team together. Very complex soil structure interaction modeling that you could do. You have to deal with the self-weight, overcoming the buoyancy, the skin friction, and the base resistance. So that's just sort of the basic concept. As long as it's big enough, it's going to go down. You'll see that they take these walls and they taper them down to a very small bearing area. And what they do as in construction is they start to excavate and create soil bearing failures, and that's how they control the sinking process. A lot of times it's very economical when you have sort of soft material that you're trying to sink through, except you have to be careful to control the speed at which it sinks. In this case, they were trying to get through, it's a glaciated area, and they're trying to get through soft material, and then they're trying to get through very hard, overcompacted, pre-compressed material. And so we started trying to figure out how are we going to approach this. I have a PhD, unfortunately, and my first inclination was, let's go model. Our senior principal said, stop. Let's start figuring out what we think will happen, and let's build up this model as we go. And I learned a ton from this project. This is when I was pretty young. We ended up creating a complicated but simplified three-dimensional shell model to look at the behavior. We worked with the geotechnical engineers. This is a case of sanity checking your inputs, but we just plotted them really quick. Does it make sense that we're putting on the right loads on this structure here in this bottom left? And we modeled the springs. But we decided instead of modeling the exact behavior, we looked at the different conditions that might happen during sinking, an ovaling condition. So we put on active spring stiffnesses and active soil pressures from 3 to 6, 9 to 12, if you think about a clock. And then we put at rest in the other quadrants, and that created an ovaling condition. We looked at the model, made sure that it's performing as intended. It is ovaling. And then we looked at the results to understand how the moment axial force interactions were happening. We also did a tilting case. Same thing, just different places of active. So we weren't trying to model exactly what happened. We were trying to say, what if this happened, bounding the solution. And one thing that we really picked up on that we were never thinking at the time when we started this work is that if you pinch the base with high pressures, you're going to put the upper part of this in tension. That came from the finite element modeling. We hadn't completely thought through it, but we saw the results and said, wait a minute, the top, everyone was worried about the failure at the bottom because that's where all the high pressures were. But the top was just constructed, it just shrunk and was restrained from shrinkage, and it got put into tension when you really pinch it. And so we realized that this failure probably happened at the top. And I will say that other experts really put together some very amazing, detailed finite element models. at the base and kind of missed the fact that this global behavior could really be one of the reasons that we saw the failure. We didn't just do that finite element model. We also did simple ring calculations. We did Rourke's formulas, so I had to do it by hand first. And so we checked a lot of this work the whole time. I think it's just a good example of building too complex as you go. So with that, I'm finished. And I think we have a good 5 minutes for Q&A. I'm wondering if anyone else is using finite sanity checks. And if there are other topics or questions that you have, feel free to raise your hand or step up to the mic. But I'm really interested to see if other people are employing other sanity checks in their system. Go ahead.
So I've been in practice for 45 years, and I have always used two methods of calculation. Computers is just a check. Actual design is done by hand.
Yep.
The problem is young engineers are not being taught in schools how to approximate the design of concrete structures. They come with computer information, but they really don't know how to design. I didn't know how to design concrete. I learned myself in practice. So sanity check is what we call approximate methods.
Yep.
And we check one against the other. So my point is, we need to lecture to schools to teach young engineers to emphasize hand methods of calculation the old-fashioned way.
I agree completely. And actually, some very simple WL²/8 checks can go a long way to making sure you've got it right. Anyone else have anything to add?
I have a question for you. When you dealt with that sinking, the caisson, for example, how do you handle the settlement between the caisson and the surrounding soil? How did you account for the slippage that takes place? Because that's one area where people do tend to overcomplicate the model, sometimes don't get it right. So I'm just curious to know, how did you guys handle it typically?
So it's a great question. It requires me to get into a different deep foundations presentation. And we actually relied on an expert in geotechnical engineering to understand what the forces would be. For our question at this situation, we were trying to understand, could the aggressive means and methods that the contractor was trying to employ to get this to go down, could it result in the kind of failure that we saw? And so we worked with the engineer to just understand some reasonable bounds when you had that soil loss. And you're correct, as you look through how this actually behaves, it becomes very complicated as you get loss into the structure from outside. If you think about it, you can't pull every timber out of there also, so you're pushing timbers as you go. So it's much more complicated, and analyzing it didn't make sense to us when we could run a simple analysis and understand the basic behavior and kind of predict that a delamination crack could happen with just a basic sort of simplified approach. And we found that it's a lot easier to argue or to sort of bolster your point when you don't have to get too complicated to answer it. Because once we get real complicated, if we get it right, we can answer it, but it also creates a lot of avenues for a difficult, in a forensic type litigation type work. So, thank you. Yeah, so one more here.
Yeah, so I think one of the major things that is not usually given attention in universities nowadays is the fact that first order analysis is usually taught in schools, while I don't think so. This is really close to reality. So second order analysis, or P delta, would alter your stiffness and would start from a deformed state. And this would largely affect your design of columns, especially because they would be deformed and they would be more prone to buckling. That's one of the things that I usually check in sanity checks. Other things are property modifiers, especially for the beams, the case where you want to actually capture torsion. So if you want to, you would compare it to the threshold torsion.
Yep.
And one other thing is cardinal points. So where, frames, join into other beams, if it's a bearing connection, or if, let's say, you have any sort of arrangement of frames. I believe those are a couple of things that come to my head while, thinking about sanity checks.
Yeah, it's a great one, and also be a little bit aware of the design, not only the finite element model itself, but a lot of the programs are now designing the members for you as well, and you want to be careful that you understand those inputs. I know that we've looked at some cases where we've had young engineers make mistakes where you specify the rebar relative to the top, and they had a negative number. They ended up having the bars up outside of the slab, and the computer model, it just says, oh, my depth is 20 inches instead of it's a slab. It was really 10 inches. So you can make big mistakes. You want to be careful that you think through it. The computer's really only as good as the input that went into it, and you want to be careful that you've checked it out. So with that, I'm going to introduce Rob McNeil.
I got one more.
Yep.
John Tahaney, Chief Structural Engineer for Stantec. I'd recommend for your sanity checks free body diagrams, lateral systems, complete load path. When I'm doing a lot of checking work, especially with junior engineers, first thing I always ask is, what's the lateral system? Draw that out on a piece of paper. Make sure they understand where forces are coming from, where they're going to, especially when you've got things like different lateral systems in different directions, diaphragms with openings, stuff like that. That can really help you out with your sanity checks. Thanks.
Thank you. I've had younger engineers who definitely are smarter than me who have said, the model's in equilibrium. It's in equilibrium. I said, yes, I know it's in equilibrium, but do you know how it got into equilibrium? And so it's an important step.